And you'll find your tests for yesterday's talk in front of you. No, you won't. Today, I'm going to continue with the introduction to complexity and tell you a little more about what's been happening recently, specifically in unfrustrated problems in quantum satisfiability. And today, I'm going to tell you about work that I've done with David Gossett, Sean Halgren, Sandeep Narayanaswamy, Marco Bardoscia, and Antonello Scardicchio. So we're going to complexity and to peel another layer of the onion and go to QMA1. QMA1 is going to be the class of problems where I can actually convince you about something so that you don't have any doubt. This is what I'm going to try today. And the problem we're going to talk about is quantum set. First, though, we will repeat and finish something that I didn't manage to do yesterday about what are the things that you can do with local Hamiltonians in one dimension. And then we're going to talk about frustration-free problems, perfect verifiers, the quantum 3-set problem, then possibly even a random quantum set and the quantum PCP theorem. So let's go and review what we've talked about yesterday. So yesterday we had a verifier circuit which could input some witness state, process it, and then output a 0 or a 1. A 1 if we believed the witness, 0 if we didn't believe it. Now we translated this problem into a physical problem about Hamiltonians, where we had a Hamiltonian whose ground state was a superposition over a history of a computation on this witness state. If nothing was accepted by this circuit, then we had the energy of the ground state of this Hamiltonian at least something. It was a high energy. On the other hand, if there was something that convinced this circuit, then the ground state of this Hamiltonian had a low energy. This was the local Hamiltonian problem where we were supposed to distinguish these two cases. And let's go and see what can be done with this local Hamiltonian problem in one dimension. So we're going to try to encode a computation. The guy computing something, psi t is the picture how he's doing after t steps, into a state that's going to be a superposition over these, somehow in one dimension. The way we're going to do it, we're going to write a Hamiltonian that checks whether, when there's a computation at this spot, there needs to be the next picture there as well in the superposition. And we're going to write it in terms of two local projectors. The projectors act only on two subsequent particles on a line at a time, meaning that when there is a state that has that reads A and B on these two particles, there needs to be another state that reads C and D. So AB changes into C and D on a line in a superposition that is a candidate for a zero energy state of a Hamiltonian that we're going to write. So the transitions, the way the things will change, will have to involve only two particles on a line. So I'll just pick a row, probably one of those rows, and we're going to try to do it there. How do I actually take some data, and before even computing, how do I move it? So imagine that I want to move your row. So one of the things that I can send a signal, you can just make a Mexican wave. So you can just wave your hands and like that goes. But this is not a two-local rule, because as the wave follows, the rule would be like this. Like if you have your hand, I have my hands raised, and you see there's somebody in front of you, then you could raise your hand, right? But this can go wrong because it goes also the other way. Whenever there are two hands that are raised already, can you help me? Like this is or three. So then you could think you could put your hand down, just like this, and this would be wrong. So a domain wall thing cannot move uniquely only with two local rules in a line. If we instead did a pulse, so meaning that just there's only one of the things that's up at a time, this can have a dead state because, for example, in this row now, everybody's sitting and there's nothing active going on. So this is something, again, that we cannot do. We cannot use a way where the data would move with nothing in front of it and nothing in the back of it, because it could just be dead. So we're going to do something else. We're going to be using several more states. So there's going to be a signal, and we're going to send this signal. So for example, you start with a signal, and then you move the signal next. Okay, that's very easy, like this. Okay. However, again, this could be something where the signal disappears and we don't know about it. So what you should do is once you send the signal, you should raise your hand that like, oh, I've already had it. This is that construction. Okay, thanks. So this is a construction that I call a surfer on a domain wall, because this is a domain wall So these guys have already had it. These guys haven't seen it before, and there's somebody surfing. But there's only one particle that's moving like this. I can check its progression by two local projectors that go and say, if you see an empty spot in front of you and you have the head on your head, you can pass it forward and raise your hand. This is what we have just done with the first row. So this is still not enough. But we're going to show the power of quantum systems on a line. That's the paper by Dorit, Daniel, Sandy, and Julia from 2006, I believe, where they have managed to come up with a construction that allows many things to move uniquely in a domain wall structure and also compute at the same time. So how can you do this? Imagine that you have this. Those are the people that have raised their hands. Then there's the people that haven't seen anything, those people on the other side. And then these guys are the data. Now, this one has a head. These ones are just have their hands down. Now, one of the rules is that you pass the head and raise your hand so the signal goes forward. As the signal goes forward, you can still see there's only one spot when there's something active. There's a single head on a person in there. Then once the head comes to the front of the row, to the front, goes down on the ground, we put it down. And now all of these guys have had the head and they're happy. Now as the head sits on the ground, there's another two local rule that says whenever there's a head and there's nothing in front of it, then a mouse comes from the ground, jumps under the head, and starts scaring the people and running away against them. So the mouse goes, and as the mouse goes, the person has to jump over it. And the mouse keeps going backwards. As it goes, it changes places with people. And as it changes places with people, then the people that had their hands up, because they've already sent the hat, they have to put their hands down. Okay? And this way, a signal went forward, changed into a mouse, the mouse came back, and then afterwards, okay, there's nobody more to scare, the head stays on the ground. And then I can just pick the head up and start the whole process again. And as you see, this data has moved by one spot in this procedure. And all of the rules, everything that was happening in there was a two local change. So two particular particles were changing into two other values. And there's one more thing to do now. When I have the data was moving, we already get it to move, and when we get it to move, we also want to compute on it, and we can compute it on it so that whenever I pick up a head at a special place, I have to do something to the head, and the head will be a computing head now, and when I have a computing head and I move it forward, then we can do a 2-qubit gate. For example, when this type of head moves forward, then we can perform a 2-qubit gate on these 2 qubits. And then when this head moves forward, I can perform another gate on these qubits, then put it down on the ground. A mouse comes, and the mouse scares us all and comes to the back, disappears, and now another person picks the head, and the whole process continues on. This is the way that you can move the data and compute on it. This is in the paper, Power of Quantum Systems on a Line. So when you summarize how many things we have 5 one-dimensional states. Those are the things that up front, in the back, the head's on the ground, and the mouse that was running back. And then 4 particles that held qubits in there. Those were data particles. So altogether, this makes 13 dimensions. And we were trying to get it to something lower, because possibly, like, could you do this with qubits? Qubits are easy. Qubits, maybe this will do something else. So one of the properties of this thing was that there was a unique state progression, meaning that every state had a particular active spot, and it was clear how it could go backwards or forwards. Everything was just connected to one state before and one state ahead. The ground state, when you look at it, if you made a Schmidt decomposition, could have been very entangled, because you see, like, these states and these states are orthogonal to each other, and then the data could be very entangled while the computation is running. And even if the computation was classical, which was what Norbert Schuch has shown, still the ground state would be quite entangled, but not too much. The Schmidt rank would be order of n. So it turns out that if you could find out matrix product states with polynomial bond dimension, you could solve NP problems. So this would be also very powerful. And one more thing that was really necessary in this construction was a clairvoyance lemma that was saying that if you imagine that you had something with fewer qubits than necessary or fewer qubits than advertised, then this state would evolve to a state that we would catch, that something wrong would happen later and we would be able to detect it. But if everything works as promised, the energy of this history state would be 0, and if the final state was accepted by a verifier circuit, then the energy of the whole Hamiltonian for this ground state would be 0. Now what we did with Sean Halgren and Sandeep Narayanaswamy is we took it down to 8 dimensions, and the way we did it, we used parity to lower the required dimension. So when you look there, there are 4 types of qubits. A qubit that is done, the qubit that is ready, then there's a qubit that has the regular head and the qubit with a computing head. Here we have only one type of qubit. Those are the blue things. And then we have these things we have seen. This is just, we've been here, we haven't been here. This is the mouse. But there's another filler one-dimensional state where basically if you have a qubit and have something in front of you, then you're ready. And if you're here and you have the filler behind you, then you're done. So basically you see that this qubit can move. Now this qubit will move, this qubit will move, but it's non-unique. So for example, what if that qubit moves at a wrong time? Immediately we will detect something that's illegal, and that will help us in this construction. So basically there are mistyped transitions, as we have seen in this 3-local construction yesterday, when we went from 5-local to 3-local. But whenever a bad transition happens, we immediately see it, its energy is high, and then instead of the history state being an eigenstate, the history state will still be a 0 energy state, because the Hamiltonian will take it away from the subspace of good states, and they will be orthogonal and will give us 0. So this is how you can get down to 8, and again, it takes lots of pages to actually prove that everything is correct, but that's the basic idea. All right, so we end up with 1 dimension, and maybe we will leave this for later if somebody wants to ask a question about translation invariant problems. Now we're going to finally turn into perfect verifiers. And turning the class QMA, where we accept proofs with reasonable probability, we reject things that try to fool us with reasonable probability, to something where we want to completely accept good proofs. So take the acceptance probability to 1 exactly, and this would be the QMA 1. That's the work that we have done with Stephen Jordan, Hirotada Kobayashi, François Legol, and Harumichi Nishimura. And now there's also been a recent paper by Perez Leni making one of the proofs better. So what are these probabilistic checks and accepting probabilities? When I'm asking this question and I'm getting a proof, I probably don't really want to be checking everything. I'm just going to, and maybe I won't even be able to do it because maybe sometimes my machinery explodes. So I'm just going to do a probabilistic check. And the probabilistic check, when my machine blows up, I'll just have to accept it. So I sometimes will accept a fake. And also sometimes there's a possibility that I will reject a genuine proof. A perfect verifier would be something that there would be a way of convincing me completely. So there would be a genuine proof, like I would get something and then look at this very little sign and say, yes, I'm completely convinced and I believe you. So this is a perfect verifier. And now I'm asking about the possibility of perfect verifiers existing for the class QMA. Circuits that accept good proofs without any doubt whatsoever. Not 1 minus exponentially small number, but with probability 1. While they still have to be sound. So when I get a fake, I should not accept it, very likely. This would be perfect completeness. So perfect proofs accepted perfectly, and fakes rejected once in a while, at least once in a while. So this is the QMA protocol. These are the 2 probabilities, the acceptance probabilities. And now I can amplify this protocol. So when these probabilities are, say, 2/3 and 1/3, I can make them go as close to 1 and 0 as possible. This is equivalent. One of the ways of doing it is just repeating the proof many times. This is what Kitaev has done. So you just repeat the circuit, you ask for several copies of the proof, and then you make a vote and see if, say, the majority of the circuits has accepted, and if it did, then you say, okay, I'm accepting the whole thing. And you can get the acceptance probability of this combined procedure with a longer proof close to 1, and the rejection probability close to 0 for fakes, or the acceptance probability of fakes. Another way of doing this would be with alternating projections. So this is a projection where you have this circuit, then you flip a bit depending on whether the circuit is accepted, and then you uncompute the circuit. There's another projection that just projects and checks whether the ancillas were 0 or not. Those are two non-orthogonal projectors, and this is what Marriott and Watrous have done in their paper, and it's very similar to what Miklos Shanta was talking about in his talk yesterday about the Jordan's lemma, when you have two non-orthogonal projections, and whatever happens there can be divided into one-dimensional and two-dimensional subspaces, and in these two-dimensional subspaces there's something going on when you repeat the things, like you make projections here and there and here and there, and depending on how often you get twice the same result in a row, then you can say what the angle between the subspaces was. And in this amplification, when the angle between the subspaces is small, then the acceptance probability for this circuit is large. So you just do alternating projections, and if you get many zeros and 0 zeros and 1 1 results, then you accept it. There's another way of doing this, and the other way of doing it is instead of making projections, the measurements, you just do reflections, and you alternate two reflections. When you alternate two reflections, that's a rotation. So again, you use the same type of thing. It's a reflection about the subspace, and this is a reflection about the subspace, and you reflect and reflect, and it's like also when you do the geometrical interpretation of Grover, you will have your state, and the state rotates. And now you can do phase estimation on this, and when you do phase estimation, you again can find out what the angle is pretty fast. And the funny thing about phase estimation, that sometimes when the phase is nice, you can get the result exactly. And when you get the result exactly, then you could possibly perfectly say what the acceptance probability was, and if Merlin told you what the acceptance probability should be, then you can check whether he was telling you things correctly, and then you could accept a proof with perfect completeness. But this is not possible all the time. So amplification is take acceptance probabilities and get them close to 1 and close to 0. Perfect amplification is take the acceptance probability of good proofs and take them to 1 exactly. Classically, this is possible, proved by Stathis Zachos and Martin Führer. So MA, the probabilistically checkable things, is the same class as when you totally accept good proofs. Quantumly, we don't know. We really don't know. And I'm going to tell you a couple of things that we have done on the way there. But on the way there to perfect completeness, there's a problem. The problem is the quantum oracle separation of QMA1 by Scott Aronson. And this oracle separation is this. When you have a box that either does identity or rotates by some angle that could be even close to 90 degrees, and you're supposed to distinguish between them, and you are promised that either this is the case, but the angle could be like from 89 to 91 degrees, anywhere in the range, or nothing. There is a very simple way of doing this probabilistically, but you cannot really do this with perfect completeness, meaning that you could be sure that you have gotten this case, even though it rotates 90 degrees, but it could rotate just a tiny bit. So if you give it a 0 as an input, and it rotates 90 plus tiny bit, and then you measure, there is a little chance that you will not get 1, that you will just get a 0 afterwards. And there just is no way of distinguishing these two cases, or getting a witness that somebody would give me and say that if you measure 1, you should accept. Once you accept something, you actually accept anything. And that's a weird thing. So we have to get around this oracle separation somehow, and we don't know how to do it. But what we can do still, quantum computation is generally thought of as something that's probabilistic, but there are ways of making quantum computing exact. And one of the ways that you might have heard about is, say, Grover's 1 in a 4 algorithm. So when you have a state that goes like this, there's a probability of 1/4 of measuring 1. When you do a reflection about 0, and then you do a reflection about the original state, you get to 1 exactly. So this algorithm, this is an exact algorithm, if you have a very precise or exact initial state. Now we can use this, because imagine that we have, for the class QCMA, where the witness is a classical witness, or Merlin and quantum Arthur. So I'm doing a quantum algorithm, quantum verifier, but the input that I get is classical. This circuit on this input has a probability acceptance P, which is not a nice number. But if Merlin could tell me a different number, a number Q, which is such that when I multiply P with Q, I get a quarter, then this circuit, which was the original circuit, combined with another one that made the probability lower, down to a quarter, when you multiply those two probabilities, and only accept here, the whole circuit like this will have an acceptance probability 1/4 on a particular witness. And if you can do this, so you have a circuit that accepts with probability 90%, and then you tell me you should turn it this much to take your acceptance probability down to a quarter. It sounds like a bad thing to do, but if you can do it exactly, then you can do this procedure where you reflect about the states that you rejected, and then reflect about the original state, and you basically do this 1 in a 4 Grover, where your state was made bad, but made exactly bad. And then you reflect, and if you can do this, you get a 1, and if you measure 1 here now, you can be sure that he gave you a correct proof, and you can accept with perfect completeness. So there is a way of using exact quantum computation for this. On the other hand, you have to be sure that when he feeds you something bad, this doesn't break. And that's possible. And this is the result that quantum, or Merlin quantum Arthur, or QCMA, quantum and classical Merlin quantum Arthur, with perfect completeness is the same as classical Merlin quantum Arthur with any completeness. We would like to get this for QMA, not for QCMA. So when the witness is a quantum state. So we would like to be able to reflect about this state, about the non-accepting states. So the states that don't get a 1, then I will get a minus. And then reflect about the state that I've gotten here. But I don't know this state because I don't know what psi is. In QCMA I knew because there was a classical information that I could measure. Now I don't know it. So I could think of, like Merlin, send us the witness and tell us what his acceptance probability is. He cannot really tell us because maybe the acceptance probability is not a number that he can just tell us directly. Maybe it's just a real number with a very difficult description and we cannot really make it. So maybe he can send us a correction state, a state that will have an acceptance probability just a tiny bit, that takes this real number to a rational number, just this tiny correction. But can we trust him? So when he sends us something and says, like, this is the correction that you should make. The only way now that we know how he can send us a trustworthy encoding of this correction is using a few EPR pairs. And that's the recent result that QMA 1 with a constant number of EPR pre-shared pairs is the same or contains QMA. So the thing is now an interactive proof. An interactive proof is something like this. I send Merlin something. So can you make something for me out of this? And then Merlin sends me something back. This would be an interactive proof with 2 rounds. I send something to Merlin, Merlin sends me something back. And then I calculate. So this is my question. When you send something quantum, so a couple of EPR pairs, this would be quantum interactive proofs with 2 rounds. And we can show that we can get something with perfect completeness now that contains QMA. So this is the class. Quantum Merlin Arthur with perfect completeness with a constant number of pre-shared EPR pairs. The way it goes, that you get this state that's a correction state, so that it corrects my acceptance probability to something nice. Merlin can prepare it by some little rotation, and the way he does it, that I send him an EPR pair, and he rotates his half by a little bit to get a Choi-Yamiokowski state of this operation. And when he gets that, then he sends this part back to me, then I can do a measurement where I take this 1/2 of the EPR pair and my input, and I measure, and whenever I get 5 plus, then on the output I get 0, or this state that's rotated by a tiny bit. So Merlin can help me make an unknown operation in a probabilistic and heralded way, so that I know when it succeeded, and he cannot fool me. But for this, I need to share entanglement ahead, but only a constant number. So this is the result. QMA is contained in the class where you share a constant number of EPR pairs and you accept things with perfect completeness. Why am I so obsessed about this? Well, because I really wish this would go away. I would really like QMA to be contained in QMA1, which would mean that the two classes will be equal. It is because there are two problems that have somehow a different nature. And actually at the QIP, yes?
Question first. What about the small probability that the interpretation using the Choi-Yamaguchi scale fail? Like you repeat a constant number of times, but it doesn't always form the gate.
Okay, so does it always form the gate when I have the Choi-Yamaguchi state of the gate? There's a probability 1/4 that it succeeds. And it's enough for me, like when it fails, I just accept the witness. I need to have a chance of catching when he's trying to fool me. So I do have a chance of catching it. That's all. So at QIP, at the rump session, I actually thought I had a proof of this. There was a proof by misunderstanding, because I misunderstood the paper that I have presented. That was not my paper. And I thought, like, why didn't they do this? And then I really thought it was working. And I worked hard on this. And then I sent it to the Japanese guys, and it was not working. And I changed things, and I figured something out, and it was not working again. And this repeated 3 times, and it's not working. So the question remains open, really. And why I would want this to work? Because local Hamiltonian, which is a complete problem for the class QMA, is a problem that's frustrated. So that means that I'm looking at, for ground states of a Hamiltonian where maybe some of the conditions are met and some of the conditions are not met, and it's hard for me to tell which. While quantum set is a frustration-free problem where I need every condition to be obeyed. And I can turn an unfrustrated problem into a frustrated, that's a simple subset, but I would like to do this backwards. So you give me a Hamiltonian for a condensed matter system, and I would want to change it into a frustration-free Hamiltonian. And I don't know how to do this. But if these two classes were equal, I would have a method for this. So that's why I'm interested in that. Yes?
I guess somehow you still have to be a bit careful, because for two local things, then you have to have frustration for, because like quantum sat for two local things in qubits.
Okay, so I cannot really think about this in qubits, because for qubits this is easy and this is hard. So somehow possibly changing a qubit local Hamiltonian, qubit 2 local Hamiltonian into a 5 local quantum set with something. Okay? So surely there won't be just a totally simple translation. But even having one, and we don't have any right now. We cannot really make everybody happy. Okay? Quantum set is a problem where I get a list of k local projectors. For example, a projector on the state 0, 0, 0, get another projector, another projector, another projector, and so on. And then I ask, is there a state that's consistent with all of these projectors or in the kernel of all of those projectors? So if I keep projecting stuff out, is there something that's left over? This is the quantum k-set problem. Is there a state where I apply all of these projectors to it? Each and every one of them will give me 0. That's quantum sum. It's an unfrustrated problem, and we know that it was QMA1 complete because, why is it QMA1? Because when you give me the state, I have to verify, or I can verify, that each and every condition is met exactly. And if it's met exactly, I can totally accept it. So it's not an approximate measurement that you need to make, but whenever you give me a ground state, each condition is perfect. And I could make the measurement perfectly, so I could accept it perfectly. So this was a problem about the quantum 3 set with a qubit, and a qubit interacting at a time. Then there was, in my thesis I've shown that 11-dimensional qubits on a line when they're interacting 2 at a time. So before we had 13, and just a couple minutes ago I showed you an 8-dimensional thing, but that was frustrated. This is unfrustrated. And then a two-local problem when you have a three-dimensional qubit and a five-dimensional qubit that's shown by Lior Eldar and Ode Dregev in 2008. And now I'm going to tell you the thing that we've been waiting for the last 6 years is take this to quantum 3 set, so actually having three qubits interacting at a time. And it was not so easy, and that's why I have really set up 20 minutes for this, and I'm going to tell you how this happened. So we're going to show how you can encode the computation into a ground state of a quantum sat Hamiltonian, which is unfrustrated. I need to be able to encode in an instance of a problem like this a computation with H and T, which are single qubit gates, and possibly a C-node, or a 2-qubit gate. And whenever I have a verifier circuit that perfectly accepts some witness, it would mean that that instance of quantum 3 set would have to be totally satisfiable and unfrustrated. On the other hand, if a verifier circuit made out of these gates didn't like to accept anything, then this instance must be frustrated. That's my goal, and that's what I'm going to try to do. The way I'm going to do it, I'm going to have, again, a list of states, which this corresponds to data at different times in the computation, and clock states. And I will need to be able to go from one state to another, or enforce that if there is one, there must be the next one exactly, with only 3 local interactions. So I need to run the clock, which we've seen that was kind of hard, and apply a 2-qubit gate at the same time with looking at 3 qubits only. The way we're going to do it, I'm going to tell you a way to construct a funny clock. So there are a couple more wheels compared to yesterday, because we're actually going to do things in superposition, and it's going to be fun. So this is what we have seen. That's a domain wall. A domain wall is a clock written out in unary, where the terms that check whether the clock is proper are terms like 0, 1. You will never see an empty and a full one here. When you want to proceed with the clock, you need to look at 3 qubits at a time. So the transitions are 3 local, and you can check whether they were applied with this projector. But this was 3 local only for moving the clock, not interacting with the data at all. The pulse clock was a clock with a single active site, where the transitions were 2 local, just like this, simple hopping. But it needed initialization because the pulse could have just died off and we wouldn't be able to tell whether it's there or not. Of course, in a frustrated system you can tell, because you can tune your Hamiltonian so that the subspace with a single excitation is preferred. But now we're talking about a quantum set or an unfrustrated Hamiltonian where you cannot enforce locally that there's only a single excitation in your system, like this. So how do I make a clock that 2 locally I can make it go forward, but it will be unique? This is how. First, take a usual unary clock. Then I'm going to move it apart into triplets. Nothing happened yet. Now I'm going to cut some of the triplets away. So still you see the structure. It's kind of like the ones are going forward. Then I'm going to replace the 111 in the original unary clock with a superposition. This is all fine so far. And I'm just going to rename some of the triplets. Are you with me so far? So we have something that's looks like a unary clock, but instead of being 111000, I'm having triplets that are just some names. I can check whether this is of this particular form, because, for example, you see a state like 001 never appears here. So I make sure that no triplet is a 001, or here, 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 and there. Then I can combine triplets and check how they go forward. So, for example, I look at these 3 things, and a 000 is okay, but for example, I will never see a, what do I never see on these 3? I never see a 111, no? Ooh, I cannot say at the moment. But there are ways of making sure that how these things are combined so that they go in proper order. And now when you look at these two lines, I'm not reading them as whole lines, but only this particular, for example, 1, 0, 0, and this continued, 1, 0, 0, 1, 0, 0, and this. They differ only at three spots. This line and this line. Which means when I write a projector onto this state, which is 1, 0, 0, but a small, because there's more of this than of this line, because this is a superposition, minus 0, 1, 1 on these guys, a superposition of these two will be orthogonal to this. A particular superposition. And only a weighted superposition where the weights of these two states are the same. So I can use three local projectors to ensure that whenever this guy exists, this guy has to exist there as well. I'm ensuring that only this part exists. But other projectors are saying whenever this exists, this must exist as well. So I can take those, just what's happening, these two lines and these two lines are getting together. And I'm going to call this superposition of all these things a clock state time 2, and I will call this a clock state time 3. And this is a 1, and this is a 4. And I will view this as my new clock states, somehow in unary. What you see, it still has this structure of a domain wall, like this is where I've been, this is where I haven't been, and this is where the active spots are. But instead of having 1, 1, 1, 0, I'm having a superposition of many things in there. But still it's possible. And now when you look, how much is there a difference between these two, how much difference is there between these two lines? Only 2 qubits differ. So when I now write a projection that will hate antisymmetry on 1, 0 and 0, 1 on these 2 qubits, I'm ensuring that this guy and this guy have to appear in the superposition with the same weight. So now I move from one clock state to another clock state by looking at 2 qubits at a time, while the clock still has the structure of a domain wall. And this is really something new, because before we could move a domain wall clock only with 3 qubits at a time. So now we had to take a couple times, join them together, stack the others together, and now these two next to each other are connected only by looking at 2 qubits. So the way it was, again, before the clocks that we were constructing had like little tiny steps. Now I'm joining them together, and I'm writing projectors that like connects the first step in the previous time with the last step in the next time. And this way I can move the clock too locally. And there's one more thing that I need to do, but probably I'll just skip it to make the clock even a little more complicated. I won't do this. But what I can do is I can locally find whether the time has already ran past some place. I can locally move the clock forward, and I can locally apply a gate. I didn't show you how to do this yet. I will do this now. So far we're up to here. The way one can decrease locality in applying gates is something called the railroad switch. Imagine you have a pulse that runs on a line. Now, I'm going to imagine that this is a train that comes to a train station, and there are 2 train tracks. 2 tracks that either it could go on the top track or on the bottom track, depending on the value of a guy that sits here and tells you which way to go. So, if this qubit is a 1, then the pulse can go only on the bottom track. If the value of the director or conductor or whoever is there is a 0, it can go only on the top track. But as you see, this can be done 3 locally. So this is the director and the 2 places where the pulse was going. Now I have all the time in the world on this bottom track to do whatever I want to a target qubit. So as the pulse on the bottom track moves forward, I can flip the target qubit 3 locally, and then join and go back here and continue. And this applies a C0, because if this is 0 and the pulse goes this way, nothing happens to the target. And if the control is 1, then it goes on the bottom way, and on the bottom track I actually flip a target qubit. So that's a C0, which is applied 3 locally, which is nice, but this needs initialization. So this pulse could, again, disappear, and everybody would be sitting and nobody's excited about it. Also, a funny thing is that then later when I invented this, I found this in Feynman's paper already. So he has an image like this. All right. Now I will want to do something like that, but not with a pulse, but with a domain wall. So I want to have a railroad switch that goes on 2 tracks, but which leaves a path. So either it went this way or that way. So when I look somewhere here, and these are empty spots here, and full spots there, I know that there's a domain wall somewhere in here. Or for example, when there's an empty spot here and a full spot here, I need to be able to ensure that an excited state is somewhere in here. How do I do this? This is something like the double slit experiment in physics. So I have 2 slits, and I need something to go through without being able to tell which way I went. So for example, these 2 things could go and interfere. This is exactly what I want. Now, I could do something to the system on the top track. This is what I want now, and I want them to interfere. However, what happens if they're leaving a track behind? Possibly, when I know that they haven't been here yet, I know they have been here, but maybe they can disappear in the system. And if I actually measure which way they went, like on the left side or on the right side of the puddle, then I really know which way they went, and there's no interference, nothing coming this way, if I know what happened. And that's a problem. So how do I combine a railroad switch with a domain wall clock? And you can do this if you, instead of 1 clock, use 2 clocks. So imagine that I have a 1 clock register that's like a horizontal clock, and 1 clock register that's a vertical clock. And you just go, and somehow you can move on this grid, and when you're here, you don't know whether it went this way or that way. However, you know that you went. Somewhere in here, like when you check these guys, we haven't been there yet, and we have been here, and both of these have the domain wall structure, you know that you're somewhere inside. And that's the trick. And now there's one more thing that you can do. You can, going from here to here, you apply a gate that does this, the lightning gate. And when you go from here to here, you do the thunder. So in this way, if you will go this way, you apply lightning first and then thunder. On the other hand, if you go this way, then you apply them in the other way. And if these 2 things don't commute, you applied 2 different gates on the 2 different types of tracks. And now all we need to do is we need to just get some control into play. And there is a way of making these transitions controlled so that when the control is 0, the only way that you can move in this clock system is this way. And when the control is a 1, the only way to move is on the bottom track. And then all together, with these double 2D clocks, you get something like the railroad switch with a domain wall structure. So you can actually tell that you are inside the system, and after you pass, you get to interfere. And that's it. We end up with quantum 3 set, where I have 2 clocks. I first will write projectors that rule out some combinations of clocks. So for example, these states will be forbidden, so that I end up only at allowed clock states like this. I will connect them. I will connect them in a very complicated way, so that like this part will involve the evaluation of a C0, and this part will involve the evaluation of single qubit gates. And all together, if everything goes as promised, if Merlin gives me stuff that was a good witness, then the uniform superposition over all of these clock states with appropriate data states will be a 0 energy eigenvector of the Hamiltonian. This is doable, and in the null case, when he tries to send me something wrong, I need to prove soundness, and this is why the paper has 40 pages, is that I need to show the promise gap is large. And the way you do it, you use a projection lemma a million times. First, you rule out bad clock states. Then you rule out these bad connections between the clock states. Then you have 2 clocks, and there will be other states. then there are things where the computation didn't go properly on this gadget inside, and you do it many, many times, and in the end, when there are no solutions to the problem, then the ground state energy or of the Hamiltonian or any state has an energy that's high, and this is how we show that quantum 3 set is QMA1 complete. If anybody's interested in the details and wants to have some fun with it, please come and talk to me. Okay, this is with David Gossett. This is mainly his work, really. And I have two more topics that I'm going to talk about, and that's random quantum set. And random quantum set is the problem where instead of having projectors that somebody prepares for me, I pick them randomly. So I pick random triplets, and I also pick random projectors. And what turns out, just like in classical set, if you put this problem can be satisfiable if there's too few conditions, and I add more and more conditions, and as I keep adding them, at some point this problem becomes unset. And I can get interested in the statistical physics of this problem and try to find the set-unset transition, see if there even is a phase transition or something that would look like it there. And one of the ways that I can deal with this, or with what we have done recently, is that we can find an upper bound on this transition. So to know that whenever there's more conditions than this, there surely will be no solutions for a typical instance of quantum 3 set. And this is what this picture means. This tells me how many conditions I have, and these are the number of solutions for the different ways I assign these conditions. These peaks, for example, would be when I assign the conditions classically, because classical set, the number of solutions. Classical set is a subset of quantum set. So when I add more conditions, the number of solutions goes down. But still, there is a particular instance, classical instance, that say has some solutions are still there. There are other quantum instances where the solutions don't exist. And what we can show that if you have a quantum set instance, the conditions are quantum. If they're classical, there should be more solutions than for the quantum problem. And if they're classical, but still worst case classical, which is something called the adversary set. So then the classical islands in the sea of quantum problems, when they're all underwater, it really means that there will be no solutions possibly to the quantum problem as well. So we use the worst case classical to put an upper bound on the transition for the quantum problem. And this is a problem, this adversary set, where you get the connections of who's connected with who, and you're trying to figure out, can you make a problem with these connections for me so that it has no solution? So how do I even figure out that there is no solution? You give me something, and I have to show that there's no solution. So this is one level higher in the hierarchy, in the polynomial hierarchy of problems. So this is random set. Finally, I'll talk about a little bit on one slide about quantum PCP. So quantum PCP, or first PCP, will be something where I can check a proof probabilistically. This is one of my failed attempts at proving that quantum 3 set was QMA1 complete, like sometime way back when I worked on this with Sergei Bravi. So it would be nice if you have a proof and you just look at a couple places and you immediately know that like this is all wrong, it just can't work. Translated in the language of Hamiltonians, it would mean that when you have a local Hamiltonian, in the yes cases of the local Hamiltonian problem, you have a low ground state energy, and in the no cases, you have a high ground state energy, and what's between them is a promise gap. A quantum PCP theorem would say that if this is made out of m terms, out of many, many, many terms, that have, like, say, norm 1, then the promise gap, if it was on the order of n, this would be the quantum PCP theorem. It would mean that basically, in the ground state of no instances, pretty much every term is frustrated, reasonably. Okay? So it's enough to look at the local observable and find out that there's just no way. If this local observable is not happy, then the whole state will not be happy, and the energy will be low. On the other hand, if this goes down and the energy is low, it would mean that there's very little frustration, so pretty much everybody has to be happy. So I could, if you give me a witness, I could just measure a couple terms, even a constant number of terms, and then determine at random, whether you're giving me a correct ground state or not. That would be the quantum PCP theorem. And we really don't know. And also, just currently, we can show that this problem is hard, not when this promise gap is like this, but when this promise gap goes like 1 over m cubed, say. And the reason for this is what we have talked about yesterday, that this promise gap is intimately tied, or we calculate it from the eigenvalue gap of the Hamiltonians that are involved. And the only way that we can encode computation, so actually then show QMA completeness of problems, is in this history state type construction. And a history state type construction has necessarily a gap that goes like 1 over L squared. So, or it goes like with the number of gates, polynomial down. So if anybody knows and would have any idea of how to encode a computation in a different way, we would be very excited. One of the ways we know that what you have to be careful about is don't do something that would make cloning possible, as we have seen yesterday, but something else than the superposition of the over the snapshots over the history. And that would be interesting. So there are many results now about the possibility of the quantum PCP theorem. We know that it would be not possible with some commuting Hamiltonians. We know something about the degree of the things and about the locality. And the expert on this probably, she'll be here next week, or she should already be here. Dorita, I don't know if you're staying, go and talk to her about the quantum PCP theorem. And also Fernando had the result that he was showing how it also will not work earlier this week. Okay, so we have shown how local Hamiltonians in one dimension work, and that finding their ground states can be very hard. Then we have shown something about perfect verifiers, and found that the problem is hard again, and there's still stuff to do. Then I've shown you how to construct a clock that can progress too locally, and that can somehow make a railroad switch go in a guaranteed way, again, just too locally, and when you have a too local something going, you can interact with another gate, and together then you can make a too local gate, like a C0. So quantum reset was QMA1 complete. Then I just gave you a little taste of random quantum set. This was the work with Antonello Scardicchio and Marco Vardoscia. And this is another big area where there still needs a lot to be done, because for random set we can ask, we know when there are product states that exist, we know when there are no solutions, we know when the Lovász local lemma tells us something more about when solutions exist, at which ratio, but we don't really know their nature. We know they probably are entangled. We're trying to squeeze these things, but we're far away from actually being sure where the transition is. So there's a lot of work to be done there. And we just really, really swept the quantum PCP theorem under the rug. And that's the news about quantum satisfiability. Now, thank you for your attention. Any questions for Daniel?
So I'm just trying to kind of connect to the topics of this workshop. I mean, do you think there's any prospective techniques from random matrix theory being useful for analysing random quantum set?
Okay, so is there any way of connecting random matrix theory with the random set? Definitely there's some randomness in it. However, one of the weird things, what happens in the random quantum set is that it actually doesn't really matter which projectors you choose. So when I was doing the numerics for the first time, I could even choose the same projector everywhere, and I was getting the same number of solutions, same dimensionality of the solution subspace. So this is kind of weird, and this really translates into the geometrization property, which means that whether a random set, quantum set, will have a solution or not, does not depend on what you choose, it only depends on who interacts with whom. So it's a graph property. So then it translates into a property of random graphs. And there, we don't know what can happen there. So we need to do something about solutions and connect it to graphs. And use properties of random graphs. basically how often it is that like some subgraph will exist. If we could show that on this subgraph we could tune the conditions in some way. So in some way, it's like pretty much every instance of random quantum set is the same. And classical instances are very special, and we use them to bound the transition.
Any questions? Well, if not, then let's continue again.
Good appetite.